Welcome to EDU World Space.
A diffraction grating is often the element that you use to look at the spectrum of a light source. And how it works is basically it is a set of very closely spaced lines, multiple ones of them. So it creates an interference pattern on the screen. And the more higher density of slits that you have, so it's basically a multiple slit device. And the more slits that you have for which the light is illuminating the slits, the better the resolving power, because each slit helps the interference pattern become clearer. So what we're going to be doing is using some diffraction grating equations to determine how far apart on a screen, well, essentially how far apart angular-wise, the two wavelengths that are in the sodium light doublet will fall. So let's take a look at the diffraction grating equation. Diffraction grating equation, sometimes just called the grating equation. And it's essentially the same equation that you use for the Young's double slit. That is d sine theta equals m lambda, where d is the spacing between slits, theta is the angle from the central part of the grating, so we're illuminating the grating. And theta measures the angle that the interference pattern essentially makes to that central line. So let's put a screen in there. I think it'll be a little bit easier to talk about, but you have interference maxima that appear on the screen, and theta gives the angle for each maximum from the central portion. So M is basically a maximum counter. It's called the order, and it's 0 for the central bright peak, and it becomes +1, -1, etc. as you go off from the center. So one of the things you notice is, of course, that the angle gets larger the bigger the order is. That's a very natural thing. The spacing between the slits actually comes from the specification of the grating. So let's call that the density of lines. D is 1 over the density of lines in the grating. So usually these are specified. For the grating that we're going to be using, we have 300 lines per millimeter. So the distance between splits then is 1 millimeter over 300. And yeah, that's a pretty small number. It is 3.33 micrometers. So yeah, these are very closely spaced lines. The lambda, of course, is the wavelength. So we are going to find the theta for each of our two sodium doublet wavelengths. So theta A is 2. So we're interested specifically in the second order. Where do those fall on the screen? So we have 2 for our M. Let me give myself a little bit more room to write 2 times 588. And I'm actually going to write my wavelengths in micrometers. So basically divide by 1,000. That gives us 0.588997 micrometers over 3.33 micrometers. And then we need the inverse sign. And basically that gives us, I better write down some significant digits because these are going to be very close together. And we do a similar thing for our second wavelength. And we get another very close angle. So we can see that these angles are very close to each other, the difference being a very tiny fraction of a degree. So one way you can get them resolved is to put your screen far away, but you still have to deal with the fact that light is going to diffract through the slits and possibly blur your pattern. So this is where the resolving power comes into play. The resolving power of a grating is given by a ratio between the average wavelength sending through and the difference in very closely spaced wavelengths is equal to the order times the number of slits illuminated. So you could have many, many slits there, but they really will not help you resolve unless the light actually goes through those slits. So this resolving power relationship will tell us about how much your beam needs to be spread over the grating in order to help you resolve the pattern. Okay, so let's solve that for n. And m is 2. For the wavelength, we could just kind of use an average. I'll just kind of take a shot that it's about 0.589 micrometers. The difference in the wavelength, we just take the difference there between the two, and we get very small amount, a fraction of a micrometer. Let me check that number. So take 5.58. Yeah, that makes sense. And we'll again write that difference in micrometers, and the m is 2. And kind of working that out, that turns out to be n is equal to 500 lines. And knowing that that's approximate, it's actually 493 lines. And it's okay if you illuminate more. you will get better resolving situation. So kind of looking back at the spacing between the slits is 1 millimeter over 300 lines. So by multiplying that by 500, so let's see, size of illumination should be equal to 1 millimeter over 300 lines times roughly 500 lines. So your spot should be, and it doesn't have to be a dot, but you will have to spread it across a number of slits by a couple of millimeters. Okay, so if your diffraction grating was, let's make the slits this way, your spot would have to be stretched out over 1.67 millimeters. That's pretty small, so fairly feasible to do.